That's when you start studying.
All right. So between today and Friday, we're going to finish Chapter 8, which means next Monday we're going to be review for the test, and the test is next Wednesday, a week from today. And based on your quizzes, you need to be studying now, because your quizzes sucked. Woo, really, really bad. The average was a 50, which means a good portion of the class got less than a 50. So, so I would start studying now. Pretty much like tonight. Tonight, start studying Chapter 1 and 2 stuff, and then maybe come back and do some 7 and 8s. So, your class wasn't the only one. My 1 o'clock class, equally rough. So, that's my friendly reminder. Go ahead and get to it. Because you'll find it takes you longer to study this than you think it's going to. On the mastering, once we've completed the homework, you can go back and redo it as many times as you want. Like, it's still open, so you can keep doing the problems, and it'll tell you if you're right or not. Or, I'm hoping by this afternoon I'll have a practice test up on the website. It's done, I just haven't had a chance to post it yet. So there's going to be a practice test on my class website that you can, not Viking Web, my regular faculty website. There should be a practice test up there. That'll tell you kind of the types of questions I'm going to be asking. So, and you can always redo your old quizzes. That's also helpful. So, the exam is usually like a third multiple choice. The rest is usually calculations and maybe some short answers, kind of like you've been doing your homework. They'll be like, what was the homework question the other day? What does lithium, sodium, magnesium all have in common? All right, they're all in the same column, which means they all have the same properties. They're all alkaline metals. Any of those things would be true about them. They have the same set of valence electrons. All of it's true. So, what can we then say about lithium, sodium, magnesium, and how we can use the quantum mechanical model to explain what ions they would choose to form? So, I don't know why there's an extra A in there. Okay. All atoms in a column. Oh, plus you can go back and watch any lecture video because they're all posted. You can go back and watch, if you're confused, go back and watch a lecture you may have missed. All right, so all atoms in a column will have the same number of valence electrons. Oh, it's not up there yet. Oh. I thought I'd turned that on. I was so excited the projector worked on the first try that I forgot about the screen. There we go. So let's look at, for example, let's look at a noble gas and then do some comparisons. All right, would you prefer to do neon or argon? Neon. All right, neon has 10 electrons. So what is the first orbital that will fill? Yep, 1s. And how many electrons go in there? 2. Okay, what comes next?
2s.
2s. And how many electrons can I put in there? Okay. What comes next? 2p. And how many goes in there? 6. All right, I got 6, 7, 8, 9, 10 out of electrons. What's interesting about these noble gases is that they have completely full orbitals. Right? So if I'm looking at neon or argon or xenon, what would they all have in common in terms of number of valence electrons? They'll all be the same number of valence electrons. How do I know which ones are the valence? What should their N value be? The biggest or the smallest? Biggest. So for this example, what N value are the valence electrons? 2. Right, these guys are the valence. And so all noble gases will all have a full set of valence electrons. They'll have a full set of 8 in that orbital. So neon is in row 2, so it has N equal 2. If I move down to 1, 2, 3, 4, 5, if I move down to xenon, right, it would be 5s2, 5p6 as their valence electrons. All same. It got really hot in here, didn't it? All right, so now we can talk about ions and how do we get to an ion. So elements with electron configurations close to a noble gas are the most reactive. Is they want to have a full orbital. All right, so we'll do sodium since we just did sodium. All right, so sodium has 11 electrons. So its electron configuration would be just like neon's. +1. All right, so it has 11. If noble gases have a full orbital, what does sodium need to do to get to a noble gas-like configuration? It needs to lose an electron. What charge would I give that? Positive charge. What then could I say about rubidium? What charge is rubidium most likely to have? It's number 37. What charge should that guy have if it's an ion? +1, right? Because it has one more electron in its valence shell. And it wants to lose it to look like krypton. So everybody in the first up and down column, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, are all going to be +1s. Bless you, bless you. They're all going to be +1s because they all want to lose that most excited electron. Well, if I scoot over to the other side of the periodic table, and we'll take a look at fluorine. If fluorine has atomic number 9, how many electrons should it have? 9 electrons. Okay, so 1s2, 2s2, 2p, 5. Does it have a full orbital? No. What does it need to get to a full orbital? It needs to gain an electron. So how many electrons would it have then? 10. And what charge would I give that? -1. So then it would be 1s2, 2s2, 2p6. So then what charge should bromine have? If it's number 35, what charge should that guy have? Same thing. So everybody in that column, fluorine, chlorine, bromine, the halogens, all the halogens should always be -1. So they only need one electron to get over to a noble gas configuration. What if I'm looking at magnesium, calcium, strontium, that column number 2? What's it most likely to do to be like a noble gas? Is it going to gain 6 or lose 2? Lose 2. So then what charge would those guys be? +2. So everybody in the second column is +2. What if I'm looking at oxygen, number 8? Should oxygen gain 2 to look like neon or lose 6 to look like helium? Gain 2, so oxygen should always be -2. Ions explained. Now that makes sense because now you can look at the periodic table and be like, oh, what do I have to do to have a noble gas-like configuration? And that should help you figure out what charge that ion should have. Oh, last thing. Use a different color. All right, so neon with its configuration, and sodium with its configuration, and fluorine -1 with its configuration, they're all identical, right? They all now have 10 electrons. We call those isoelectronic. So it's elements or ions, right? So in this case, I'm comparing neon to 2 ions. So it's elements / ions with the same electron configuration. So neon, sodium +1, and fluorine -1 all have the same electron configuration. How come they're not the same element? What makes an element unique? Number of protons. Now, I haven't done anything with protons. I've just messed around with the electrons. So isoelectronic mean that they all have the same electronic configuration. Good there so far? Good, good. Okay. Okay, there's a lot of words on this slide, so I'll go slow. All right, so now we're moving into periodic trends and how we can predict how an element is going to behave based on where it is on a periodic table. And so the chemical and physical properties of each element is a periodic trend, right? So how it behaves. Everybody who's a halogen acts the same. Everybody who's an alkali metal acts the same. If you're in the same column, you're going to behave similarly because you have the same number of valence electrons. So there are going to be 4 properties that we're going to look at that occur periodically. You can make some extrapolations about how they work. The first one we're going to look at is atomic radius, and also look at how ions, how their radii occur periodically. We're also going to look at effective nuclear charge, ionization energy, and something called electron affinity. And all of these properties have a periodic trend, meaning they occur every so many elements. We can make some predictions about what's going to happen next. Or if we look like radii, we're going to say they increase, going left to right, up to down to up, things like that. And let's see, which one do I have? I'll wait for everybody to catch up writing. Okay. All right, so atomic radius is going to be our first property that we're going to look at. The atomic radius is the average radii, bonding radii, between 2 atoms that are not bonded to each other. In other words, I have 2 atoms just hanging out near each other. About how big around are they? All right, because if they bond to each other, then it's harder to look at because they're sharing their electrons. All right. Here are the trends, and then we'll talk about why these are true. So atomic radii peak at the alkali metal column. As you move down a column, I guess that should be radii increase. And as you move left to right across the periodic table, or across a individual row, the atomic radii decrease. All right, so let's think about why these trends are the ones that are true. So let's compare. What are two elements to compare? Let's look at sodium versus chlorine. All right, I would like to know how many valence electrons sodium has. A few different ways you can think about that. You could either write out its electron configuration, or you could say it's in column number 1, or you could say it's one past the noble gas. Any of those would be correct. So how many valence electrons should sodium have? 1, right? Plus, we literally just did this problem like a slide ago, so you can always just flip back. What if I'm looking at chlorine? How many valence electrons are in chlorine? 7, right? Because it has this electron configuration. So all of those are valence. So it has 7 valence electrons. Now I lost what page I was on. All right, so if we were just thinking about size, right, it'd be a little confusing if it has more electrons. Why would the radius decrease if I'm going across? All right, because this one has 1 valence, this one has 7 valence. So it doesn't make a lot of sense if we're going across that it's actually getting pulled in tighter. So how do we explain how that is? So let's look at, since I'm going to draw a picture, I'm going to choose lithium because it only has 3 electrons. You can certainly draw it for sodium with all 11 electrons, but my picture is going to be a little easier to see with just 3. So how do we explain this trend? So for a multi-electron atom, every electron experiences the positive charge of the nucleus as well as the repulsion from the other electrons in its orbital. Right, so it's kind of feeling 2 different things. It's feeling pulled in towards the nucleus, because right there's positive charge there. At the same time, you can't get too close to the other electron because they're the same charge. So they have to push away from each other. This repulsion by the other electrons, this part right here, this repulsion from or by the other electrons, shields each electron from feeling the full effect of the positive charge at the nucleus. I'm going to flip my paper over here in a second and draw a picture. Maybe the picture will help. All right, so let's say I have, right, we were using lithium. So how much charge should my nucleus have altogether? If I have lithium altogether. Yep, plus 3 altogether. All right, because it has atomic number 3, which means it has 3 protons, so plus 3. And this is a terrible sketch. Orbitals don't actually look like this, right? They don't actually look like circles, regardless of what you learned in high school. Orbitals are not all circles. But for now, we'll draw them as circles. So how many electrons would be, if I call this 1s? How many electrons would I put in my 1s orbital? 2. Right, they each have a charge of -1. Where do I put my next electron? In a 2s. All right, something like that. So based on what we know about energy levels, this 2s1 electron is the farthest away from the nucleus. Just in space. And so these 2 electrons here in the 1s2 orbital, or the 1s orbital with 2 electrons, are each feeling the most of this positive 3 charge. Right, so closest to it, they have the biggest draw towards it. This one up here is farther away, and there's only a +1 charge left over, right? Because each one of these are using up each +1, and so there's only a +1 charge left over. And so since it is the farthest away, the 2s1 electron, and doesn't feel particularly a lot of charge, right? +1 is exactly equal. It's not going to be held as tightly to the center as some of the other, as compared to like the 1s, right? The 1s can't go anywhere, so they're core electrons. So that 2s1 electron is not held on as tightly. And so it makes the radius larger. Since this 1 electron is not being pulled in very tightly, it has the freedom to kind of float far away, make the radius really large, relatively large. Right? It has the freedom to kind of float away, pull in, float away, come in. That is not true if we look across to fluorine. I did something for fluorine. And again, these are not particularly good sketches. Right? They're definitely not accurate. So what kind of charge would be in a fluorine's nucleus? It has atomic number 9. How many pluses should I have in there? Also 9. Right? And then it would look similar, right? It would have this 1s, then it would have the 2s. And then this is where the sketch gets kind of weird, right? Because s's are spheres, but what shape does p have? Yeah, it's like the dumbbell shape. So it's actually kind of like a little bit this. In 3 dimensions. And so I have 2 electrons over here, my 1s. And I got 2 electrons over here, my 2s. And then I have 5 electrons scattered. 3, 4. Scattered throughout there in 3-dimensional space. Because you now have these p orbitals that are kind of more up, down, left, right across the sphere, they are pulled in closer because they are passing fairly close to the nucleus at all times. Right? If we go back, wherever you look back at your other thing, the 2 lobes are on top and bottom of the nucleus, all right, and they jump from top to bottom without going through the nucleus. So they're being held in closer. These 2p electrons are being held in closer to the center. They feel more charge. So the radius is smaller because they have less freedom of where to be. Yeah.
And is that just because of their shape? Like because of the shape of the orbital?
Partly because of that, and partly because I now have +9 in the center. And right, so more positive charge. So each electron feels more than just +1. It really feels like +7.
Okay.
Right, because in the s orbitals, which are spheres, I've used up 4, let's see, 2, 4. Okay, so I've used up 4, and so really +5. So each one of these electrons in the p orbital are feeling +5, so they're pulled in much closer to the center. So they have less ability to spread out because they're being sucked into the center. So the 2p5 electrons are feeling, what did I just say, 9, a +5 charge. So if they're pulled in closer, should my radius be big or small? Okay. Yeah, so it has a smaller radius than lithium. So that's the trickier part. Yeah.
So in the 2s part of the fluorine, would those ones be not held as tightly since they're spherical? Like the
I'd say relatively held less tightly. Yeah. Yeah. So they have a little more freedom to move around. But overall, the whole thing's being sucked in tighter. So that explains going left to right. Let's now think about going top to bottom. So if we look at lithium compared to cesium, all right, so lithium's number 3, cesium's number 55 in the same column, has the number of valence electrons changed? No, how many valence electrons would it have? 1, right? It's in the first column, so 1 valence electron. What has changed in terms of quantum numbers, going from row 2 to row 6? N. N has changed. And what does N tell you about the quantum number? It starts with an E, ends with a Y. Energy! It tells you energy, right? So I've gone from a maximum of 2 energy levels to a maximum of 6 energy levels. So how much bigger would I have to have my radius to have 6 energy levels in it? Bigger to have cesium or bigger to have just 2 energy levels? Sheer number of electrons. You can also think of it that way. I have to have a spot for 55 electrons versus a spot for 3. Which one should have the bigger radius, 55 or 3? 55 should have the bigger radius. So that's what we see in our trends of atomic radii. It is in your textbook someplace. So we are looking at lithium versus fluorine. All right, so lithium has a radius of 152, pretty big. Fluorine has a radius of 72, so that's less than half. So even though it has more electrons, I went from 3 to 9 electrons, it has shrunk by half. That's because it has more charge and each one of those electrons are being sucked in tighter. But if I look at lithium, I guess they don't even have cesium on here, rubidium. Lithium compared to rubidium, rubidium has 37 electrons compared to 3. So this, because they're all one valence electron on the outside, that last electron is really, really, really far out there. Because if rubidium has a atomic number 37, what should the charge of its nucleus be? I'm trying to throw out some softballs here. 37 also. Good. Okay. So if it's a positive 37 on the inside, and 36 of the charges have been used up by all the other electrons, that last electron is really, really far away and it's feeling very little positive charge, which means it's super easy to take away to become rubidium plus 1. So atomic radius kind of plays into what becomes an ion. That last ion, or that last electron, isn't being held very tightly, which means it's easier to pluck off and make it into a plus 1 charge. It's like that last little kid, like you have a whole bunch of kids on your little string. That last one, number 37, you may not see all the way down to the end line. He may wander off. You're down 1. You shouldn't be in charge of 37 kids by yourself. But if it helps you think about that. All right, so how do we feel about atomic radii? All right, let's talk about, what do I have next? I guess I have effective nuclear charge next. All right, so this plays into what we just talked about. Z effective, which is code for effective nuclear charge. When we're talking about atomic numbers, what letter did Z tell you? Did it tell you the mass, the atomic number, or the element symbol? It told you the atomic mass. And the atomic mass tells you how many about what? Does it tell you about the electrons, the neutrons, or the protons? Protons. So the effective nuclear charge, Z, is the number of protons. So it's saying how many protons is any one individual electron feeling, being attracted to. So Z effective is the positive charge felt by an individual electron. So we just talked about shielding the core electrons shield the valence electrons from feeling the full positive charge of the nucleus. Sorry, that should say core. That C looks crazy. All right, so see if I finish that. Yeah. So we can calculate the Z effective by comparing the number of core electrons to the number of valence electrons. And the larger the Z effective, the stronger pull, I guess is a good word, the stronger pull of the nucleus on those valence electrons, which translates to smaller atomic radius. All right, so a fancy table we're going to fill in. Pretty exciting. To help us kind of see how Z effective changes as we go across the periodic table. All right, so starting with sodium, which we just did, right? Sodium has 11 protons, 10 core electrons. 11 minus 10 is 1. And then I went to this picture over here and wrote down 186. All right, let's do magnesium together. Oh, question first.
So is the atomic, I'm going to do atomic mass. Because last slide you said atomic mass, but here it says atomic number.
Definitely number. Number of protons.
Okay.
Sorry.
Okay, that's okay.
I was thinking mass for something else. Yes. Atomic number of protons. Z. Z protons. Mm-hmm. All right, so let's look at magnesium. What is magnesium's atomic number? 12. How many core electrons does magnesium have? 10. What would that then make the effective nuclear charge? 2. So would we expect the radius to increase or decrease if now the Z effective is getting bigger? It should decrease, right? Because each electron is now being pulled in tighter, which we do. Using your chart over here, it's now 160. All right, let's look at aluminum. How many protons does aluminum have? You should see my snazzy trend on my fancy chart. How many core electrons does it have? Still 10. So then what should Z effective be? 3. You guys are so good. Not even using a calculator or anything. Aluminum, 143. All right, last one. Let's look at silicon. How many protons does it have? 14. How many core electrons? Still 10. So then what's the Z effective? 4. So should the radius be smaller? Yes, it is. It's actually 118. Yeah.
How did you get the numbers in this last column?
I went back. I looked at this little table. You wouldn't know them. But I just wanted to show that Z effective is increasing and the radius is decreasing. Increase going across, and the radius is decreasing. So they're, I guess, opposites. As the effective gets bigger, the radius has to get smaller because each electron's being pulled in tighter. All right, we'll have time today to just start ionic radii. We won't be able to finish it, and we'll finish everything else in Chapter 8 on Friday. So looking at ionic radii, ionic radii is the radius, radii, should be radii, either a cation or an anion. What charge do things that are called cations have? Those are the positive ones. What about things that are anions? Negative. Okay. What two columns are guaranteed to be cations across your periodic table? You can for sure say that the first two are always going to make cations. What are those first two columns called? They both start with A's. We have the alkali metals, and then the alkaline earth metals. 1 and 2. What column, or what name of the column, it'll be easier that way, what name of the column should always be an anion? Halogens. Halogens guaranteed always to be anions. And it's because of their electron configuration, right? They only need one more electron to become negatively charged. Or they have a full orbital. Bless you. So at the gain or loss of an electron, we expect the radius must change size. All right, so we already talked about atomic radii if everybody's all neutral. But now we're going to either add an electron to make an anion, and we're going to take one away to make a cation. Okay, we can do one of these this morning, and then we'll do the other one, and the rest on Friday. All right, choices, cation, anion, which one do you want to do first? Cation, great choice, all right. All right, so if I have a cation, which is positively charged, have I gained or lost an electron? You've lost an electron. All right, so let's look at, we've been doing sodium a lot, we'll just do sodium again. All right, so that's regular sodium plus 1s2, 2s2, 2p6. So how many protons does regular sodium have? 11. How many protons does sodium plus 1 have? That's how many electrons, how many protons? If its atomic number is 11, how many protons does it have? All right, still 11 protons. So I've gone from 11 electrons, 11 protons, to 10 electrons, 11 protons. Here, we're feeling a Z effective of 1, right, because each one's 1 to 1. Is the Z effective going to be greater or smaller now that I've lost an electron? Is each electron going to feel exactly plus 1, or is it going to feel more than plus 1? It's going to feel more than plus 1, right? Because here, there's exactly 1 proton per 1 electron. Now I have more protons compared to electrons. So the Z effective has increased or decreased? The Z effective's increased, because now I have more protons per electrons. So if the Z effective's increased, which way should my radius go? Get bigger or shrink in? It should get smaller. All right, so Z effective is increased because each electron is going to quote-unquote feel. Electrons don't actually feel. We use the word feel. They feel more than a plus 1 charge. So if Z effective is increased, that means the radius decreased. When Na becomes Na plus 1. So comparatively, the ion is smaller than the normal atom. All right, we will save the rest of the stuff for Friday. I have your quizzes again in alphabetical order. It's easiest for me if I just call you alphabetically.